Hello students. Today we shall work out some examples from the textbook of optics by Brijlal Subramaniam and Avadhanalu on the chapter Interference. The first example is green light of wavelength 5100 angstrom from a narrow slit is incident on a double slit. And if the overall separation of 10 fringes on a screen 200 centimeters away is 2 centimeters, find the slit separation. Okay. So the given parameters in this example is the wavelength of light is given. So wavelength lambda is given as 5100 angstrom. In meters, it is written as 5100 into 10 raised to minus 10 meters. Okay. And it is incident upon a double slit. If the overall separation of 10 fringes is 2 centimeters. Okay. So here I have the expression for fringe width beta. Beta is written as width of n fringes divided by number of fringes n. So here it is 2 centimeters divided by 10, that is 0.2 centimeters. In meters it can be written as 0.2 into 10 raised to minus 2 meters. Okay, and in that sentence we have the screen is placed 200 centimeters away. So I have capital D distance as 200 centimeters. That is 200 into 10 raised to minus 2 meters. That is 2 meters. Okay, so the given parameters are written down. Now we have to find the slit separation, that is small d, is to be calculated. Now from the given parameters, we know that the expression for fringe width beta is given as lambda capital D divided by small d. So this implies that we can write small d is equal to lambda capital D divided by beta. Substituting the terms, I can write 5100 into 10 raised to minus 10 into 2 divided by beta is 0.2 into 10 raised to minus 2. Now calculating this, I can write 5100 into 10 raised to minus 8 into 2 divided by 0.2 is 10. We have 5100 into 10 raised to minus 7. That is, small d can be written as 0.51 into 10 raised to minus 3 meters. That is, the slit separation small d is 0.51 millimeters. Now, in the next example, we have two coherent sources are 0.18 millimeters apart and the fringes are observed on a screen 80 centimeters away. It is found that with a certain monochromatic source of light, the fourth bright fringe is situated at a distance of 10.8 millimeters from the central fringe. Calculate the wavelength of light. Okay. Now, in this example, the given parameters are that two coherent sources are a small d distance apart. It is given as small d is equal to 0.18 millimeters. So in meters, I can write it as 0.18 into 10 raised to minus 3 meters. And the fringes are observed on a screen placed at a distance 80 centimeters away. So capital D is given as 80 centimeters. That is, in meters, I can write 80 into 10 raised to minus 2 meters. Now, for a particular wavelength of light, the fourth bright fringe is situated at 10.8 millimeters from the central fringe. So in Young's double slit experiment, we know that the distance of a fringe from the center is assigned as x. So the equation for x was given as, distance of x from the central fringe was given as n times lambda capital D divided by small d. Now here the value of n is assigned as 4 and all the other parameters are given. Here x is given as 10.8 millimeters, and that in meters can be written as 10.8 into 10 raised to minus 3 meters. Thus, rearranging this expression, I will write lambda is equal to x small d divided by n capital D. That is, here x is written as 10.8 into 10 raised to minus 3. Small d is written as 0.18 into 10 raised to minus 3 divided by n is 4, capital D is 80 into 10 raised to minus 2. Okay. Now calculating all these parameters, we get 0.006075 into 10 raised to minus 6 plus 2, so 10 raised to minus 4, right? Wavelengths are usually can be written in terms of nanometers or angstroms. So writing it in angstrom, I will have 6075 into 10 raised to minus 6 into 10 raised to minus 4. Hence, wavelength lambda, it can be written as lambda is equal to 6075 into 10 raised to minus 10 meters, or 6075 angstrom. Now in the third example, we have interference fringes are observed with a biprism of refracting angle 1 degree and refractive index 1.5 on a screen 80 centimeters away from it. If the distance between the source and the biprism is 20 centimeters, calculate the fringe width when the wavelength of light used is 6900 angstrom. Okay. Now the parameters given are the refracting angle of the biprism. So we have alpha is equal to 1 degree. We have to convert it into the SI units, radian. So 1 into pi by 180 gives it in radians. The refractive index of the biprism mu is given as 1.5. Okay. The screen is placed from the biprism at a distance of 80 centimeters. Now that distance is usually assigned as small b. Okay, small b is equal to 80 centimeters, or 80 into 10 raised to minus 2 meters. See, in this experiment, we have the source to be the slit and we keep the biprism in front of it. Okay, and then we have a screen placed further apart. Now here it is said that we have the screen at a distance of 80 centimeters from the biprism. Okay, and this distance is usually denoted as B, and the distance of the slit to the biprism is denoted as small a, and the total distance from the slit to the screen is denoted as capital D. Okay, so small b is given as 80 centimeters. Now if the distance from the source and the biprism is 20 centimeters, that is small a is 20 centimeters, that is 20 into 10 raised to minus 2 meters, I can immediately write capital D as A plus B, that is 80 plus 20, 100 centimeters, that is 1 meter. Okay. Now, what do we have to do? We have to calculate the fringe width when wavelength of light used is 6,900 angstrom. Again, given parameter is lambda 6,900 into 10 raised to minus 10 meters. Now, to calculate fringe width, we have the expression beta is equal to lambda capital D divided by small d. Now, small d can be written in terms of refracting angle as 2a into mu minus 1 alpha, right? Now, substituting for these terms, we can write lambda 6,900 into 10 raised to minus 10. Capital D is 1 divided by 2 into small a, 20 into 10 raised to minus 2 into mu minus 1. Mu is 1.5 and 1.5 minus 1 is 0.5 into alpha is pi by 180. So we can write this as pi by 180. 180 goes into the numerator. Now, calculating the numerators and denominators, I can write it as 19,777.07 into 10 raised to minus 8. We can rewrite it as beta is equal to 0.197 into 10 raised to minus 3 meters. Okay, so I have taken 10 raised to minus 5 into this term and written the 10 raised to minus 3 remaining term here, and this is millimeters, so beta becomes 0.197 millimeters. In the next example, we have the biprism experiment. Here in a biprism experiment, the eyepiece is placed at a distance of 1.2 meters from the source. So distance from the eyepiece to the source is capital D. It is given as 1.2 meters. Okay. The distance between the virtual sources was found to be 7.5 into 10 raised to minus 4 meters. Again, small d is given 7.5 into 10 raised to minus 4 meters. All are in SI units itself. Now find the wavelength of light if the eyepiece is to be moved transversely through a distance of 1.888 centimeters for 20 fringes. So the last line implicates the fringe width. Okay. So the distance moved for 20 fringes is 1.888. So from the expression of beta, we have width of 20 fringes divided by 20. So the width of 20 fringes is 1.888 centimeters divided by 20. That is 1.888 into 10 raised to minus 2 divided by 20 meters, right? Now, we have the expression in terms of lambda, capital D and small d for fringe width as beta is equal to lambda, capital D divided by small d. Now, from this expression, I can rewrite lambda is equal to as small d beta divided by capital D. That is lambda is equal to, substituting the values, I write 7.5 into 10 raised to minus 4 into 1.888 into 10 raised to minus 2 divided by 20 divided by capital D 1.2. Okay. So calculating this, we get 0.59 into 10 raised to minus 6 meters. Okay. Now, usually wavelengths are written in nanometers or angstroms. So converting this into that unit, I can write lambda is equal to 5,900 into 10 raised to minus 10 meters. That is 5,900 angstrom. Now, in the next experiment, we have a light source emitting lights of two wavelengths, 4,300 angstrom and 5,100 angstrom. So let me write the parameters. Lambda 1 is equal to 4,300 into 10 raised to minus 10 meters, and lambda 2 is equal to 5,100 into 10 raised to minus 10 meters. Now this source is used in a double slit experiment. The distance between the sources and the screen is 1.5 meters. So capital D is given as 1.5 meters, and distance between the slits is 0.025 millimeters. So small d is given as 0.025 millimeters. That is 0.025 into 10 raised to minus 3 meters. Calculate the separation between the third order bright fringes due to these two wavelengths. Okay. Now each of the wavelength or each of the color produces its own interference pattern. Okay. So that is why the question is that we have to calculate the separation between the third order bright fringe of both the wavelengths. So from lambda 1 we have a pattern, and in that pattern we have to find out the third bright fringe, and in the second pattern, which is due to lambda 2, we have to find the third order bright fringe in that and find the separation between them. Okay. Now in Young's double slit experiment, we saw that the position of the bright or dark fringe can be represented as x is equal to n times lambda capital D divided by small d. Okay, so here we have two fringes due to two wavelengths, lambda 1 and lambda 2, and we are going to find the difference between the two bright fringes from these two patterns. Okay, so let the bright fringe, the third order bright fringe due to lambda 1 be represented by x1 position. So we have n is equal to 3 into lambda 1 into capital D is 1.5 divided by small d is 0.025 into 10 raised to minus 3. Okay, so calculating it, we have 180 into 10 raised to 3 lambda 1. Okay, now x2 is the position of the third order bright fringe due to the second wavelength. Now for that we have x2 is equal to n lambda capital E by small d, that is n is 3, lambda is lambda 2 into capital D 1.5 divided by small d 0.025 into 10 raised to minus 3. Calculating it again, we'll get 180 into 10 raised to 3 lambda 2. Okay, so the difference or separation between these two third order bright fringes are x2 minus x1. Okay, that is given as 180 is a common term, 180 into 10 raised to minus 3 into lambda 2 minus lambda 1. Now the differences in wavelength is substituted as 5,100 minus 4,300 is 800 angstrom. That is 800 into 10 raised to minus 10. So this can be calculated as 144,000 into 10 raised to minus 7. That is 0.014 meters, or Fringe width, usually we calculate fringe width with the eyepiece in terms of centimeters or millimeters. Okay, so the differences in these two third order bright fringes can be written in terms of centimeter as 1.44 centimeters. Okay. So today we have worked out a few problems. Understand the theory behind it, learn it well. Next day we shall work out a few other problems. So that's all for today. Thank you.